In section 9.2, we discussed two specializations of the general alternating optimization algorithm, called the Blayhat-Arimoto algorithms. We first discussed the algorithm for computing the channel capacity. Let Rx times Py given x be a given joint distribution on alphabet x times alphabet y, such that R is strictly positive, that is, Rx is strictly positive for all x. This is illustrated in the diagram at the bottom. Here Rx is the input distribution to a channel Py given x, where the random variable x is the input random variable, and the random variable y is the output random variable. Let Q be a transition matrix from alphabet y to alphabet x, that is, a transition matrix in the reverse direction. Now consider this maximization of a double summation, summation x, summation y, Rx times Py given x times the log of Qx given y divided by Rx, where the maximization is taken all Q such that Qx given y is equal to 0 if and only if Py given x is equal to 0. This double summation looks rather complicated, but note that all the quantities in blue are given. Lemma 9.1 says that the maximum of this double summation is attained by a transition matrix Q star, where Q star x given y is equal to Rx times Py given x divided by summation x prime, Rx prime, Py given x prime, where the numerator here is the joint distribution of x and y, and the denominator here is simply the marginal distribution of random variable y. And so, Q star is equal to the conditional distribution of x given y. That is, the maximizing Q is the reverse transition matrix that corresponds to the input distribution R and the transition matrix Py given x. Now in the double summation on the right-hand side above, Rx times Py given x is simply Qxy, and for the fraction inside the logarithm, the numerator Q star is equal to Qxy divided by Qy, and the denominator Rx is equal to Qx, the marginal distribution of random variable x. So this fraction is equal to Qxy divided by Qx times Qy. And so the double summation is summation x summation y Qxy log of Qxy divided by Qx times Qy. That is the mutual information between the input variable x and the output variable y. We now prove lemma 9.1. In equation 2, let the denominator be wy. Assume without loss of generality that for all y, Py given x is greater than 0 for some x. Otherwise, we can simply delete that y from the alphabet y. Since the input distribution R is strictly positive, wy is strictly positive for all y, and hence Q star x given y in equation 2 is well defined. Rearranging equation 2, we have Rx times Py given x is equal to wy times Q star x given y. For any reverse transition matrix Q satisfying the constraints in equation 1, consider the double summation evaluated at Q star minus the double summation evaluated at Q. Now this Rx and this Rx cancel with each other, And upon combining the two double summations, we obtain summation x, summation y, Rx times Py given x log Q star x given y divided by Qx given y. Using the relation in step 4, we replace Rx times Py given x by Wy times Q star x given y. Now Wy does not depend on x, so it can be moved outside summation x. And the inner summation, that is summation x Q star x given y log Q star x given y divided by Qx given y, is simply the divergence between Q star x given y and Qx given y. And evidently, this is greater than or equal to 0. The proof is completed by noting that Q star, as defined in equation 2, indeed satisfies the constraints in equation 1. It is because Wy is greater than 0 and R of x is also greater than 0. Therefore, Q star x given y is equal to 0 if and only if Py given x is equal to 0. That is the constraints in equation 1. Therefore, Q star as defined in equation 2 is indeed the maximizing Q. We remark that the maximizing Q in lemma 9.1 is indeed unique. Toward this end, we note that in order for the inequality in step 5 to be tight, Qx given y must be equal to Q star x given y for all y, which implies that Q must be equal to Q star. Theorem 9.2 says that for a discrete memoryless channel Py given x, the channel capacity is equal to the supremum over all input distribution R that are strictly positive, the maximum over all Q of summation x summation y Rx times Py given x times log of Qx given y divided by Rx, where the maximization is taken over all Q that satisfies equation 1 in lemma 9.1. Note that by lemma 9.1, this maximization is actually equal to the mutual information between the input and output of the channel. Compared with the original definition of the channel capacity, we see that we have replaced the maximum over all input distribution R by the supremum over all strictly positive input distribution R. We now prove theorem 9.2. Since the mutual information between x and y depends on the input distribution R and the transition matrix P of the generic channel Py given x, we write Ixy as IRP. Then C is equal to the maximum of IRP over all input distributions R. By lemma 9.1, we see that the maximum of the double summation over all Q in the formula in theorem 9.2 is indeed equal to IRP. Therefore, we need to prove that the maximum of IRP over all R is equal to the supremum of IRP over all strictly positive R. That is, the maximum over all input distributions can be replaced by the supremum of all strictly positive input distributions. Let R star achieves the above maximization. If R star is strictly positive, then in C, the maximization over all input distributions R can be replaced by the maximization over all strictly positive input distributions R. This, in turn, can be replaced by the supremum over all strictly positive distributions R. Next, consider the general case that R star may not be strictly positive. That is, there may exist zero probability masses in R star. Since IRP is continuous in R, for any epsilon greater than 0, there exists a delta greater than 0 such that if the Euclidean distance between R and R star is less than delta, then the gap between C and IRP is less than epsilon. In particular, there exists R tilde greater than 0 such that the Euclidean distance between R tilde and R star is less than delta. This is illustrated in the figure below. Here, R star is on the boundary of the probability simplex. That is, there are some zero probability masses in R star. This is the case of interest because the other case, that is R star is strictly positive, has already been treated. Now consider a ball of radius delta with the center at R star. And R tilde is a probability distribution within this ball. Following the definition of C, we have C equals the maximum of IRP over all input distributions R, which is greater than the supremum of IRP over all strictly positive R. Since R tilde is strictly positive, this in turn is greater than or equal to IR tilde P. As R tilde is within a distance delta from R star, we have C minus IR tilde P is less than epsilon, or IR tilde P is greater than C minus epsilon. In the above chain of inequalities, by letting epsilon goes to 0, this goes away, and so we conclude that the supremum of IRP over all strictly positive R is indeed equal to C. This completes the proof of the theorem.